2D kinematics is really about keeping up with motion in the x direction and the y direction. Most famous example is to take an object, put it at some height, give it some horizontal velocity, and just watch how it moves. And now mathematically describe how it moves. We do that with something we call the position vector r. So if we were to sort of plot what we just saw, we'd say, okay, let's start at some initial height y, make it go this way, it'll start out flat and then it'll fall kind of like that, increasing slope. Keep in mind, this is not a kinematics plot. This is not time. I'm now plotting where it was in y, where it was in x. We would describe that with a position vector r, which you could write like this. X position I hat, y position j hat. But that x and y, those are functions of time. Those would describe how those positions change in time. And the r vector, if you wanted to draw it, would just change in time. There's the r vector at one point in time. There's the r vector at a later point in time. It started out right up the y-axis like that and just came down. That's how we could start. This could describe any crazy motion, but we actually want to describe this case that you'll see in your homework a lot, which is constant acceleration. So if we're going to describe constant acceleration, we go back to our 1D kinematics and how we described x in 1D. And what was that? It was x initial plus the initial velocity in the x times time plus 1/2 the acceleration in the x t squared. So I'm putting x on everything because this is just the x component. That's I hat plus, and now the same thing in the y. The initial y plus the initial the y initial velocity. Let's see, I'm going to say vyi, so I should probably say vxi there. Times time plus 1/2 the acceleration of the y times squared j hat, just fit. Okay, so that's the general expression you would use. But then you'd say, I know some of these are 0. So then you look at your problem. So now this is for the chalk toss, this specific chalk toss. And we could simplify a little further. We could say r equals, let's see, we gave it no initial position, so xi is 0. We gave it an initial velocity, and I can draw it now, vxi, it looks like that. So we would still have vxi, t, and there's no reason to have an acceleration in the x. If we're just thinking about gravity, that's only in the y. So really we just have the initial x velocity times time I hat. And now in the y direction, we did have an initial height, yi, so we can leave that there, yi. And we gave it no initial vertical velocity. We said we threw it horizontally, so vyi initial is 0. And we do have acceleration in the y, the gravity pulling it down. So we're going to go ahead and put in negative 9.8 for ay, so minus 1/2 g, 9.8 meters per second squared t squared, j hat. So for this specific problem, that really is the position vector. And you can use that to solve sort of anything about the problem. For example, if you wanted to know the velocity at a certain time, like what's the velocity vector look like when it hits the ground, you could get the instantaneous velocity from this expression. This is the instantaneous position, so v would just be dr dt. And remember that these unit vectors are just constants, so you can just ignore them. So the velocity at all times would be, this derivative is just vx initial I hat. And here, derivative of that is 0, so this would be minus 2 times 1/2, so it would be, and that's just g, so the derivative would be minus gt j hat. So there is the velocity at all times. And if you wanted to know the velocity when it hits the ground, you would just have to figure out the time it takes it to hit the ground and plug that in for t. And why not? Let's get the acceleration as a check. It's dv dt. The derivative, 0 on the I hat, no acceleration in the x direction as we would expect, and derivative of that is minus g j hat, which if you consider g 9.8, of course that's correct. So that's really how you do it. This is the special case, though, I'll point out, when you often think of the two directions as separate. You'll often be told, oh, you can treat these completely separate. And that's true for most physics problems you're going to do, because usually you have constant acceleration and it's just in one direction. And in that case, they do act completely separate. That does not have to be the case. You can have physical effects happening where they would be coupled, and the problems just get a lot more difficult, so we don't do them. But an example would be if you thought about wind resistance or air resistance. That kind of drag sometimes goes as the speed. It doesn't care what the two components of the velocity are, it just cares about the speed. So that's a case when your drag force, and we'll get into forces later, when your drag force in x might depend in some ways on the velocity component in y. And then these two things would depend on each other, and then it's a mess. So in most problems you do, especially in a 2D kinematics chapter, you can think of them as completely independent.